Dr. Chen, the floor is yours.
Thank you for a nice introduction, and also thank you for organizing this workshop and the good lineup. Because the previous speaker provided a good application and results for apply this meta learning to communication systems. And in my talk, I will mainly focus on the theoretical understanding about meta learning for the pre-trained models. So if we think about many recent advances in machine learning, a lot of it comes from using gigantic models, which involve billions of parameters. And when training those models on those big data sets, they often generate the intelligence that can surpass human beings, for example, in those image, speech, and video tasks. And however, if those breakthroughs in those tasks are often difficult to translate into real-world application engineering systems, because a massive number of training samples are typically very costly to obtain in those engineering systems. For example, the communication system, which is the focus of our workshop today, the deep learning has been applied to this communication system to overcome the limitation of model-based approach in different settings. For example, the channel estimation, demodulation, encoding, decoding, and power control. But in many engineering value systems, such as those in smart homes and autonomous vehicles, this is a picture I adopt from the Northeastern flash testbed about various systems for autonomous vehicles. And labeled data in those systems are very limited. For example, in IoT, those devices will transmit short packages with very few highlight symbols, which had also been mentioned in the previous talk. And in those cases, the question is whether those deep learning models can still be powerful with few highlight symbols to estimate the channel and also for subsequent tasks. So in this context, pre-trained models serve as a warm start of model training to overcome the limitation of data scarcity in those engineering systems. Broader speaking, a pre-trained model is any model that trained on broader data set at scale and can be adapted to a wide range of downstream tasks. And for the communication systems, we can think of those the task as, for example, estimating the channels for a particular device, and we can do a pre-training on a bunch of devices and transfer this model to another new device joining the systems. And for example, the recent popular language model GPT-3, maybe some of you may already use that by your interest, and is one type of pre-trained models, and it often outperforms the model trained from scratch in terms of sample complexity. For example, with the same number of parameters, the pre-trained models have higher accuracy. So in this talk, we are particularly focused on one type of pre-trained model, although there are many methods that can do the pre-trained large models. For example, those unsupervised learning methods, but we will focus on the meta-learning based pre-training models for this task. The idea of meta-learning is to use the training data sets from multiple tasks to learn the inductive bias, such as the model initialization for the downstream new tasks. So first, in the pre-training stage, we have T tasks. You can think of the task as the pilot labels from the T devices. And then we will simulate the adaptations, that the uniqueness of the meta-learning pre-training is that it simulates how the model will be adapted in the new tasks. So it was in the pre-training stage, it simulated that this model theta 0 will be adapted to theta tau on task tau. And then it will minimize cost function to find a best pre-trained model that will do a good job in adapting to the T task we observed. And in the testing stage, we were using the pre-trained model from the pre-training stage, and then adapt to the new task using the adaptation data, and then evaluate in the testing data. And there are many different meta pre-training methods. They mainly differ in how they take into account the adaptation step in the pre-training. So for example, the MAMO model agnostic meta learning, which has been already mentioned in the previous talk, considers one step gradient as adaptation step. For example, we have a common pre-trained model theta 0, and we take one step gradient descent to obtain the task-specific model parameter, and then we evaluate the loss on these task-specific fine-tuned models. And there are other methods called implicit memo algorithm, which differs in how they adapt the pre-trained model theta 0. In this case, it solves a regularized optimization problem to do the fine-tuning stage. And in this case, if the alpha goes to 0 or gamma goes to infinity, these two meta-training method will reduce to a joint learning step, a joint pre-training method, which essentially find a common pre-trained model for all tasks. So in this talk, we are particularly interested in the generalization capability of the pre-trained model. So we measure the performance of the pre-trained model by the so-called test risk. So we first do a pre-training using a bunch of observed tasks to get a empirical pre-trained model theta 0 hat. And then we will plug in this theta 0 hat in, then adapt in the new task and evaluate the performance of the new fine-tuned model parameter in the new task. And this is a so-called task risk and a test risk. And test risk can be decomposed as a minimum risk and the excess risk. So this minimum risk is basically measured by the infinite number of samples. It measures how good the meta-training objective is. And this excess risk is caused by the finite training samples in the meta-training stage and measure how good the generalization capability of the pre-trained model is. So this is the way we evaluate the performance of the generalization of the pre-trained model. This is our starting point of the talk. And as we will have shown in the previous slides, pre-trained models are often large and overparameterized. And the overparameterization can happen either in the pre-training stage, either in the fine-tuning stage. For example, this n is the number of samples in the new task. And the d is the dimension of the pre-training model. You can think of this d as dimension of neural network, for example. And if this d is larger than n, that means that overparameterization occurs in the fine-tuning step. So this is not the worst thing to happen. But in another situation that overparameterization happens in the pre-training stage. For example, d is not only larger than n, it is larger than t times n. T is the number of tasks in the pre-training, and n is the number of samples per task. So t is so large that it is larger than the number of samples among all the tasks we collect. So we will discuss the generalization performance in these two settings of overparameterization. And the natural question is that do this overparameterized meta pre-trained model prove or generalize in these two settings? So if you are familiar with the classical statistical learning theory in the statistical learning theory class 101, it may suggest that the pre-trained model or its fine-tuned model with overparameterization may overfit the pre-training or the adaptation data sets. So this is because the classical learning theory will suggest that there is a delegate bias and variance trade-off. So this code means that so this axis is the model complexity. You can think of that it is the dimension of the model D, and this y-axis is generalization capability in the broader sense. And this curve means that if you increase the model complexity, the generalization capability will first decrease and then increase. So mean that we should not choose a model that is too large in order to achieve a good testing performance. So we want to find a sweet spot between two large models that will overfit and two small models that cannot capture all the details of the data set. However, in practice, what we observe is that overparameterization does not hurt generalization, especially in those pre-trained settings. So overparameterization is common in both the fine-tuning stage and pre-training stage. So this is a table. We collect from this popular paper of the benchmark of meta-learning, and it shows that so this row is number of parameters of different models, which are very popular for the convolutional models and the residual net models. And this row represents number of training set data in the pre-training stage. And we can observe that even in the case where the number of parameters is much larger than the training data, the performance of those pre-trained models still is very good. And in fact, the performance increase with the number of parameter increase is in this meta pre-training settings. So the message here is that in practice, overparameterized model can generalize, but in theory, it does not generalize well. So there is a contradiction between conventional understanding of the statistical learning theory and what we observe in practice. So given the classical results in under parameterized settings of statistical learning and the recent advances for generalization of overparameterized model. So we are not the first one to study the generalization of overparameterized model. There are a lot of prior work understanding generalization of the overparameterized model, especially those models training from scratch, but not in the meta learning settings. And our focus of this study is to for this following question: one, that whether it can provably generalize, meaning that if and when the overparameterized meta pre-trained model generates well. The second is that what is the sample complexity of it and how it depends on the number of tasks in the pre-training stage and the number of data per task and data covariance and task heterogeneity. So we will answer these two questions. We will answer these two questions in the next 5 minutes. So to answer these two questions, we consider the regression settings. So it is a supervised learning setting where we have a data set d tau, have a pair of supervised data x tau and y tau. And we assume that the data generation model is linear and there is a ground truth parameter theta tau gt represents the ground truth. And also we have a Gaussian noise in this data generation model. And we define the data covariance matrix as Q here. And Q can be different on each task. We adopt this linear model because there are a lot of prior work in this line also using linear model to show the generation performance of those either models trained from scratch or pre-trained models. And also this linear model can capture the scenario where we view the output of the last layer of the neural network as a feature vector X, and we fix all the weights in the first several layers. And we can be, because the reason we can treat this as a feature X is because those weights typically do not change in the adaptation stage. So we consider these models, and we first study the overparameterization in the fine-tuning stage. In this case, the problem is, if you think about this problem as solving a system equation, this problem is well conditioned. And this is a fairly simple settings. And we have very nice results. So basically the results we get is under some bounded eigenvalue assumption of the data covariance matrix. So with high probability, the excess risk of the pre-trained meta models will be upbounded by 2 terms. One term that decays as the number of tasks increases. Another depends on the dimension of the models and the decay as the total number of tasks in the pre-training stage. So in this case, because the D is smaller than the Tn, so this term will also diminishing when Tn goes to infinity. Because we consider that the case where the pre-training, the overparameterization only happen in the fine-tuning stage, not the pre-training stage. And the message here is that the method we consider the model agnostic meta learning, implicit memo, and the joint learning method have the same dependence as N, T, and D in terms of excess risk. And also the excess risk will decrease as the number of tasks and number of samples per task increases, and the increases as the number of dimension of tasks of the model increases. So this is the first result. And the second result is that we consider the setting where overparameterization happens in the pre-training stage. So in this case, the dimension of model D is larger than the total number of tasks multiplied by the number of data per task. In this case, you can think of that we're solving a system of equations where this system is underdetermined. And we have multiple solutions which can be captured simply, in this simplified case, can be captured by this flat basin of the minimum. So there are multiple minimum of the solution. So basically there are multiple solutions for these pre-training problems. So to understand the generation of the pre-trained model, we focus on this solution that have the minimal L2 norm solution because there are many evidence suggests that if we use an SGD type of algorithm to train the models in the pre-training stage, it will converge to a minimal norm solution. So although there are multiple solutions, but all other solutions are in the non-space of the minimal norm solution. So this is the solution we want to study the generalization. It is a minimizer of the pre-training problem, and also it is a minimal, have the minimal norm. So it worth mentioning that there is a concurrent work posted in the archive almost at the same time as we submit our work by the Huang Liang and Longbo's group, and also Professor Liang from OSU, that they study the generalization problem of the pre-trained solution obtained by running finite number of mammal algorithm in the overparameterized linear setting. So basically, I study a solution not in the minimal norm solution, but a solution obtained by the mammal algorithm in a slightly different settings. So in this setup, our key results is as follows. So again, under some assumption of the eigenvalue of the covariance matrix, the excess risk of our pre-trained model theta 0 hat can be upper bounded by these two, the summation of these two terms. So these two terms looks a bit involved, but let us digest a little bit. So this term will diminishing as the total number of tasks and number of samples per task increases. So we do not need to worry about this term. So this term is a little bit involved. So this V is the constant that capture the data heterogeneity, and these two terms will not necessarily diminish into 0 when Tn goes to infinity, right? Because Tn represents total number of samples in the pre-training stage. So if Tn goes to infinity, this term will go to 0, but this term is not necessarily go to 0. And so these two terms actually reflect the variance of the corresponding to the subspace spanned by the k stars largest eigenvalues of the matrix W and the d minus k star smallest eigenvalue of the matrix W. So this matrix W is a matrix that depends on the covariance, data covariance matrix Q, and also depends on the hyperparameters in the adaptation stage. So due to time limitations, we will do not have time to go through the details. But the point that in order for this excess risk to go to 0, we needed to impose some conditions that this effective rank should satisfy some conditions so that this whole thing will go to 0. And the condition that the effective rank need to satisfy means that the data matrix, covariance matrix should have several eigenvalues that is very large, and also have many smaller eigenvalues, and they are uniformly small. They will not have they will not decay very fast. So this is a rough idea of what assumption we need for benign overfitting or generalized well in the overparameterization in the pre-training state. So we need the requirements on data covariance matrix and hyperparameters. So we do not have time to talk about the case that going beyond the linear case, but the key message here is that in the nonlinear case, the landscape of loss function is much more involved than the linear case, not like this convex shape. It have many local minimums. And the way we tackle this problem is that we want to find some minima that have a flat region around the minimum, and it has been observed empirically that those flat local minimum can generalize well. And we will refer to this paper for if you are interested in, you can look at this paper for details. So just to recap, so we talk about the generation of pre-trained meta models in the overparameterization settings, and we talk about some conditions. We talk about in the setting where overparameterization in the fine-tuning stage it generates well. If overparameterization happen in the pre-training stage, we need some assumptions on the effective rank of the data. And we also ways to improve generalization in the nonlinear cases. And if we are interested in application of meta-learning to communication systems, we also have a recent monograph that's posted in archive that have a list of applications that we can use MAMO for our communication. So with that, I want to conclude and open up for questions.